All right, we are finished with Chapter 1. We're jumping into Chapter 2. This is where we begin, although 2.1 we don't do it yet, but this is where we actually begin to start solving for differential equations.
Nothing real quick about Chapter 1.
Yeah?
I don't remember if we covered boundary value problems. I remember them being mentioned.
Yeah, I mentioned them, and we didn't do an example of that. I may have done an example without the solutions, but I think the boundary problems really only come up one time in this class, and we will dive deeper into the boundary value problems when we get there. But so right now, it's just a gloss over. When we see it, we'll revisit that idea. So Chapter 2 begins with the idea of solution curves, just to get some ideas of what the solutions might look like. And they came up with, and there are, I found some websites that help us visualize or help us graph these things. Desmos might have something, but I didn't look deep enough, or I didn't research stuff. But there's two that I found a few years ago. There's four, actually, that I found a few years ago. Two of them are gone, and two of them are still here. So we'll take a look at those as examples of trying to draw solution curves. Now, these types of graphs that we're going to look at are called direction fields or slope fields. And as the name suggests, they draw out the slopes. And what happens here is that we define, we are restricted to first order differential equations, first order ordinary differential equations to be more precise. So we're just looking at dx dy or dx dt or dy dt or whatever independent and dependent variables you have. So we are focused on one type of differential equations from all that stuff that we classified from before, and that is the first order ordinary differential equations. So the idea behind a slope field or a direction field is to get a picture of how the curves might begin to look like. Now, when we take a look at a differential equation, let me come up with a differential equation, dy dx, example. dy dx is equal to negative y over x, I think is the one that I'm thinking about. Is an example of a differential equation. It's an equation with an unknown function, y, with an independent variable x, and at least one derivative that's involved. That's dy dx. And if you can somehow write your differential equation where you have dy dx on one side, you can essentially find a slope field. So remember that this is the slope, or the derivative, or the rate of change, whatever you want to call it. But geometrically, we can look at that as a slope. And the slope is dependent on x and y. Whereas before, in Calc 1, when we were doing derivatives, we took derivatives of something as a function of x, and all your derivatives are all functions of x only. But here, it's a combination of x and y. And so if we have something like this, we can kind of set up, the long-winded way of doing this is to set up a table of x and y values, which represent the point, and then we have dy dx, or f of xy, whatever that would be. And then what we could do is we can plug in values here to try to figure out what the slope might look like. So, for example, 0, 0, is it infinity? I'll just put a question mark here, because it's actually indeterminate. It's not infinity. It's not a vertical slope, but because it's 0 divided by 0, it's one of those indeterminates. So we don't want x to be 0, but we can certainly let y equal to 0, right? No, when I say y equals 0. We can certainly let y equal to 0, and x can be any number that's, as long as it's non-zero, then your derivative will be equal to 0. So what are these points when y is equal to 0? It's the x-axis. So it looks like in the x-axis we'll have a slope of 0. Slope of 0. That's a horizontal tangent line, right? Now let's make the x, or let's make the y non-zero, and let's look at the point 1, 1. What's this going to be? -1. So it looks like if my point was sitting on 1, 1, then the slope of my curve should be -1. Now, how would we picture that? So we would picture that by looking at the point that we're looking at, which is 1, 1, and then drawing a slope of -1 at that point. So let me just draw a small little line segment that looks like it has a slope of -1. Let's try another one. 2, 2. What's the slope there? -1 also. So at the point 2, 2, I'll have a slope of -1 also. Let's try something that's not the same, like the point 1, 2. How about 1, 2? What is it? -2. So this is going to be negative. Now I don't want my. This is a -1 slope. I don't want to. Wait. Where is 1, 2? 1, 2. So at this point, that's a -1 slope. What's a -2 slope look like? Is it going to look steeper or less steep? Steeper. Let me see if I can make this steeper. It looks a little steeper, right? And then let's try one more. So nobody ever does this by hand. But I just want to show you what the idea is and where these things come from. So 2, 1, it's negative what? 1/2. So at the point 2, 1, right here, then I would have another graph that's less steep. So imagine doing this work with a bunch of different points. So what are you going to get? Well, if you do it with a bunch of different points, you're going to get a plane full of little line segments that describe the slope. You're going to get a field of slopes, slope field. Actually, I downloaded the Java, what do you call it? Applet. I downloaded the applet already. So this is how your equation might look like. So they use x and t for the variables, so be flexible with that. We're using x's and y's, or here they're going to use x for the dependent variable and t for the independent variable. So looking at my equation, it looks like my independent variable is x and my dependent variable is y. So it looks like if I change that back to x and t, it looks like this is going to be x and the bottom would be t. So negative x over t. So if I ask it to graph, this is what I'll see. In this case, I even have arrows. It tells you which way it's going. But you'll see that whenever you draw slope fields, your arrows are always going to go from left to right. So this is how the slope fields would look like. And if you look at the points that we were messing around with, 1, 1, looks like we're over here somewhere, I would have a slope of 1. So this is one way to view the slope fields. And it might be good if we actually drew the, oops, where would it be? The x and y axes there. So this would be your slope field for dy dx equals negative y over x. So this wasn't the one I wanted. I wanted something else. Anyways, we're here. This is what we got. Let's move on. The other slope field that I wanted to show you was from GeoGebra. And it's the same idea. You punch in your equation. Remember that dy dx has to be solved for. It has to be by itself. And some programs, if they're nice enough, they actually have that set up so that they have this blank field for you to just type in your equation where dy dx has already been solved for. And this time they are using x and y, so we can just use minus y over x. This one has some added information here, solutions and stuff. So let's talk about the solutions in a few minutes. But this is generally how the slope field would look like. This time it doesn't have any arrows because it's really just a bunch of tangent lines. You can look at it that way. Any questions about slope fields? What are you doing with slope fields? Use them to get some idea of how the curves would look like, how the solutions would look like. Now, remember, these are all families of curves. So one thing you can do is you can imagine from your slope fields, you can imagine drawing out a particular solution. So the solution would be something where you would imagine following the arrows and see which way they go, right? If your solution happens to, if your initial position happens to be down here, and you would follow the arrows or follow the slopes. And then you get some idea of how your solution curve would look like. Yes?
But isn't it the slope field that's
Well, right now this is a slope field without any of these things, but if I start trying to figure out, trying to guess what the solutions are, then I'll get a family of solutions this way.
Even at the initial point, it would still be a rectangular slope instead of a solution. The solution is supposed to be a function or a relation.
Right. And so what we would find here is a graph of a solution. I'm not understanding your question.
I mean, all these curves are representing slopes. Right?
All these lines are representing slopes. The curves that I'm drawing would represent solutions. So I can draw a lot more curves here that follow the lines as slopes, and then those would all be possible solutions. Yeah?
I think what he's getting at, what you're asking, like when you solve one of these, like if you just want to define like a general solution to a differential equation like that, you'd integrate it, right? So you get
You do something, yeah.
you do something like that, but you'd end up with some sort of constant that tells you can like shift it around, sort of like when you're integrating. So this gives you like, this kind of like accounts for it.
All the possible, yeah.
It gives you like all the possible ones, and then when you get a specific like, oh, at start at x equals 0, it's some number, that gives you your one specific one. But this is like accounting for all of the constants you can
Right.
add in.
So I think maybe if we bring it to this now, let's go back to the idea of initial condition. Maybe this will clear things up a little bit. So an initial condition would be a starting point. We can call it a starting point, or we can actually think about it as Well, we'll write it in a couple different ways. Let's pretend it's a starting point. So give me a point anywhere except with zeros. 2, 3. So if this is my initial condition, I can similarly or equivalently write y of 2 is equal to 3. Those two things are the same. This y of 2 is equal to 3 says that I'm at the point x is equal to 2 and y is equal to 3. Right? Now, if I look over here and I go x is equal to 2 and y is equal to 3, then that would be my starting point. And then from here I can draw out, and now I have this graph, and this graph is my particular solution. To my IVP, initial value problem, where the differential equation is this and the initial condition is this. It looks like it's some sort of y equals e to something negative x squared. So if we were to work this out, if we were to actually solve for this, which it might be, but we'll solve for this by the end of today. We should be able to analytically solve for this differential equation. We'll get the exact result. Okay? Now let me go back to those programs over here. And they have this added feature where if you have a specific, if you have an initial position, initial condition, then they actually would draw out the curve for you, the actual solution curve. So let's take a look at this, and 2, 3, right? So if I click on this, then I'm going to get my solution curve, my particular solution for that differential equation. Actually, you can click anywhere you want, and then you can get a whole bunch of curves. Get a family of curves for this, right? But the particular one that we saw passes through the point 2, 3. I can do that with the other program as well.
Is the same as a family?
Say it again?
The same as a family.
No, the particular solution is only one solution out of the whole family. So the family of curves,
Represented by these vectors.
well, these vectors can help you draw out the curves.
Yeah.
Yeah. Okay.
Because the constant isn't changing in whatever equation.
Well,
It's the x's and y's that can be.
the x's and y's are the ones that draw out the graphs.
Yeah, but those are the ones we're not naming. We're just have the whole field saying, oh, all of them. But the plus c, whatever that is, that constant is like that's not changing.
In this one curve.
Just in that one curve.
Right.
Okay.
So if I change a constant, I'm going to get a different curve. And if I change another constant, then I'm going to get another curve. No?
Well, just so you're changing the constant as well as the x's and y's.
Well, when you change a constant, you're going to have a totally different curve.
Okay.
So your x's and y's is the relationship of that function, of that curve. We'll get to separable differential equations, which is the example that we have, and we'll actually pick that and then tear it apart and take a look at the general solution, particular solutions, family of curves, and all that.
Yeah, because we could just have that exact curve, but just shift it.
Yeah.
That's another scenario.
Yeah.
Not having to do this.
Yeah, but that's a different a different shift. The shift just says that's how it's.
Not necessarily a family.
That's not necessarily a family of curves, because maybe your family of curves isn't about a shift. Maybe your family of curves is about an actual changing the format of the curve or something.
It could be both.
Yeah. Or one or the other, but probably not both.
Not at the same time.
Yeah, not at the same time. Whew. All right. These are good questions. It's clarifying. I hope it's clarifying, and I hope it's not confusing people who think they might understand it already. But like I said, when we get to actually do the example and work it out by hand, hopefully it'll clear up a little bit. Now, we can continue to talk about another special type of graph. And the graph would be dealing with these things called autonomous differential equations. And an autonomous differential equation is a first order differential equation whose, if you were to write the dy dx on one side, I forgot if that's called normal form or standard form. Normal? Yeah, because standard is the one that's set equal to 0 or something like that. So a differential equation that's written in normal form, first order, then your right-hand side, if your right-hand side has no independent variables, it's all the dependent variables, then you have what's called an autonomous differential equation. Which means the slope or the derivatives are not relying, the rates of change are not relying on the independent variable. So we saw a bunch of simple examples in the past, and these are exactly what they mean by autonomous differential equations. So our very first example where we said dp dt is equal to kp, the rate of change of population is proportional to the current population. That's an example of an autonomous differential equation. We have Newton's or some other modified kind of other differential equations. I think one we looked at last time was the rate of change of a disease or something being a product of the disease times people that don't have the disease. So that would be another example of an autonomous differential equation because it has no independent variables in the right-hand side. So these are two simple examples. And with this, it turns out that your graphs of your differential equations, as you move from left to right, will be approaching or going away from some important points. And the points are going to be those y values where it's equal to 0. And in that case, they're called critical points or equilibrium points. So there's a list of facts here that you can just read through, but what I'm more interested in is taking a look at a picture of this and seeing how the picture might look like. Let's take a look at our second example over here because it has more than one 0. And by 0, I mean if you set the right-hand side equal to 0, you solve for m, that's what you get. So let's focus on that example. dm dt is equal to, we need an actual value for k, so let's just make k equal to 1. So let's try to see how we can relate the facts to this particular differential equation. Let's first find the critical points. So if we set m times 1 minus m equal to 0, we're going to get m is equal to 0 and m is equal to 1. So these are equilibrium points. And let's make it clear now that the points, when they say points here, they're not talking about a point on a graph. It's just the equilibrium point, and the point will actually be a y-axis value. So this is a y-axis value. If C is an equilibrium point, then y is equal to C is a constant solution to the differential equation. So what they're saying here in fact number 2, so number 1, number 2, they say that y is equal to, I guess, should be m, right? M is equal to 0 is and m is equal to 1 are solutions to your differential equation. So that means if I take this, take the derivative of 0, oh, that's 0, and then 0 times 1 minus 0 is equal to 0, so that works. If I take the derivative of 1, that's 0, and I have 1 times 1 minus 1, that's also 0. So they are, in fact, solutions to the differential equations. This says DE here. That's fact number, well, that's this fact right here. So let's take a look at these other facts, and then we're going to use the slope fields to help us view these facts. It says if you have two critical points and no other critical points in between, then any solution between these two critical points will remain between these two critical points. That means if my solution is between 0 and 1, y value of 0 and 1, I'm not going to go past 1 or past 0 below. And solutions must be strictly increasing or decreasing. So my solution will be increasing. If I have a solution between 0 and 1, my graph will be increasing always. And then critical points are asymptotes. So these will end up being asymptotes. Can you picture it? If you have particular solutions, or the family of solutions will have these as asymptotes. So in this case, this is what I'm kind of seeing, and then we'll confirm this with the actual graph. So this is the scenario, right? Number 3, if C is the critical points, and the solution is going to be between these two critical points. So if I have a specific solution here, I'm not going to go past this point 1, m is equal to 1. It becomes a straight line at that point. Right, it can't increase beyond that. And then if I go backwards, I'm not going to go below my critical point 0. If I, yeah?
But it only works for the ordinary differential equation.
Yeah, this is just for these special types of differential equations that look like this. All right, so if I happen to be below, down here, then I'm not going to go past 0, but I have a probability, a possibility, and probably will be going down to infinity. And then likewise, if I'm up here, then I'm going to have an asymptotic behavior towards m is equal to -1, and then this will probably go up to positive infinity. So you can see that the critical points are going to be bounded by these, the solution curves are going to be bounded by those critical points, and they're going to be asymptotic at those critical points. And then your graphs are strictly increasing or decreasing. So I have strictly increasing here, strictly decreasing here. And this one, I don't know if I drew this correctly, but the way I drew it, it's strictly increasing, but it could possibly be decreasing, depending on how this might look like. So let's take a look at how that looks like for reals now. So let's take our, do you guys have a preference? Let's use the Java applet. So my variable is x, which is x times 1 minus x, I think was the differential equation. Is that right? M times 1 minus m. All right, let's graph it. Oh, I didn't want to put any graphs yet. Well, let me just put a whole bunch of graphs here. It looks like it was increasing, so I was right. So it looks like this is a setup. If you're between 0 and 1 in the dependent axis, you're going to be increasing with an asymptote at 0 and asymptote at 1. If you're above 1, then you're going to be decreasing from infinity going down to 1. And if you're below 0, you're going to be at 0 asymptotically, and then you're going to drop and then decrease. So all those facts are satisfied, and then we have these, this family of curves. Any questions? It's really fun. You guys should really check it out.
Are we going to do any like checklist stuff, quiz-wise? Oh, checklist.
I don't know. Yeah, so it's first order differential equation. And then we have our 0 axis here. This is your t-axis. And I don't know exactly. I guess I can randomly put my m-axis anywhere. M is equal to 1. M is equal to 0. Maybe I should write that bigger. Nah, whatever. So this is a scenario, right? We have an autonomous differential equation, and they have to follow these rules. So based on your critical points, or equilibrium points they're called, we can try to figure out how they look like. So it turns out that equilibrium points, remember, these points are not really points. They're actually y values, or independent values. So in this case, m values. These m values over here are asymptotes. So there's two things that can happen in an asymptote. One is that the graphs can move towards the asymptote, or the graphs can move away from the asymptotes. Do you see these two scenarios happening here? So it turns out that if they move towards an asymptote, then that has a special name, and if they move away from the asymptote, that has a special name too. So what do you think what happens when they move towards the asymptote? The asymptote is what? What? Converging. Another word?
Magnetic.
Stable, magnetic. What? No, not positive. They're attracting. Attractive. They're fine. They're attractors. Yes, these notes will be posted. So if a solution curve approaches an asymptote, that value, that critical point, that equilibrium point that we found is called an attractor. And if a solution curve goes away from an asymptote, that's called a repeller. And there's some cases where one side might attract, the other side might repel, in which case it's semi-stable.
All left to right relative.
All left to right. We're all reading things from left to right. So it turns out
Find out without cracking it. Is there a way to find out what they were?
probably. Should I let you think about it or just tell you?
I think we don't need to know.
Oh, I'm afraid you might.
Checking whether it's positive or negative on either side.
Yeah. First derivative test, remember that? Yeah, that was a long time ago. Who'd remember
This
that?
already is the first derivative.
What?
This already is the first derivative of y. Right there.
It is, essentially. But that's not what I meant. So, in any case, now that we have this idea of attractors and repellers and autonomous differential equations, so these autonomous differential equations really just depend on a dependent variable and not the independent variable. That's kind of weird. I'm just, what am I doing? Oh, that's it. That's what I'm doing. So if we look at this scenario, really what happens in the graph stays in the graph. And then we're just focused on what's happening with the x and y, or with the dependent axis. So if we take a look at our dependent axis here and separate it, we found the critical points, or the equilibrium points, to be 0 and 1, right? And if we kind of do that, what did you say?
Check if immediately on either side
Yeah.
it's positive or negative.
So if you tilt your head to the right, to the left, sorry. Tilt your head to the left. Oh, you guys aren't playing. If you tilt your head to the left, imagine this as just a regular number line, right? And then you have your equation m times 1 minus m. And say, like Evan was saying, if we put in a number, if we put in numbers that are, you know, in between two critical points or left and to the right of a critical point, then we figure out if the sign is positive or negative. And that is essentially the slope. And we can see that the slope would be increasing or decreasing in those places. So, for example, if you put in a value like a larger than 1 into the differential equation, you're going to get 2 times 1 minus 2, which is Negative? Should be. So it would be negative. So we know that everything up on top will be decreasing. And then you put in a number between 0 and 1, like 1/2, you should get positive. And then you put in a number that's less than 0, you're going to get a negative. And then now you have this scenario, again, looking at it from left to right, or looking at it with your head sideways, it looks like the first derivative test, right? We are just looking at derivatives. So now we can denote, with one axis, we can denote whether something is a sink or, did I say sink? A stable point or an unstable point by looking at to see whether the arrows are going away or into that point. So at 1, I'm decreasing, and between 0 and 1, I'm increasing. So I can see that 1 is a stable critical point. And at 0, above it, I'm increasing. Below it, I'm decreasing. So I must be pulling away from that. It's a repeller. That must be an unstable point. Yeah?
So it's similar to the basics of the stable equilibrium.
Yeah, it's essentially the same thing. I can't erase that. Okay. So this is a one-dimensional representation of the graphs. If you have an autonomous differential equation, you can get some sort of picture to see how this graph would look like.
How are you evaluating those numbers one more time?
We're putting it back into the differential equation,
M 1 minus M.
m times 1 minus m, yeah.
So you took 2 times -1.
Yeah. And it's negative, so it's decreasing. Okay? So as another quick example, what if we had a representation that had -1, 0, and 1, and say your graphs
What would you call these sign patterns?
sign patterns.
Yeah, but you'd say it and it's like, wait, like, you'll never get out. Sign pattern.
Having some issues with your trig teacher, huh?
No, this was algebra.
Oh, even worse. So, if you have an autonomous differential equation, and all you did was this one-dimensional graph on the left side over here, by finding critical points and figuring out whether they're sinks or, I keep saying sink, whether they're attractors or repellers, right? You should be able to draw a family of curves from that. Because if it's going to be going away from 1, you know that your graphs are going to look like this. If it's going to be going away from 1 and going to 0, your graphs will look like that, right? They're asymptotic. They're always increasing or always decreasing from left to right. So they're really just going to have one shape. And this is also attracting. So this is m is, or y is equal to -1 is semi-stable. So it's going away and also going away from one side and going to on the other side. So this is an example of something that's semi-stable. Okay? So you can easily picture the slope fields or the family of curves just by knowing this information. Pretty cool, huh? Yay, whatever. Okay. Let's move on. Oh, by the way, that one-dimensional graph is called a one-dimensional phase portrait. Maybe I should put that in our notes too. And if you have, in our example, if you have an autonomous differential equation, all you need to do is figure out what the phase portrait is, and you should be able to figure out how the graph would look like. Okay? All right, let's move on. Another section, 25 minutes. Separable, yay. So let's actually do some differential equations now. So writing out the definitions of some of these things might be a little bit cumbersome because it's usually easier to actually look at an example and see how it's done. But mathematically, it's always important to try to articulate the conditions that you need for a particular technique. So in this case, a first order differential equation has a form of dy dx is equal to g times f, where g is a function of x and f is a function of y. And writing it like that's kind of weird, but the important part is that you can separate it. And that's the main key here. You can separate the differential equation into the independent variables on one side, including the differential dx, and the dependent variable on the other side, including the differential dy.
That form right there is not separated yet.
We're not separated yet. It becomes separated when we actually, separate it. So dy divided by f of y is equal to g of x dx. So now this is separated. So a lot of the things, the autonomous differential equations are really separable differential equations that we can do. And the example that we were looking at earlier was also another example of a separable differential equation. So I'd like to start with that to hopefully tie in those slope curves that we were looking at, or the general solution, the slope field, the general solution, and particular solution. So let's do our example. I had an example here, but I'm going to switch it to our first example, which was negative y over x. Is that it? I hope this is I hope this is easy. Sometimes when you plan things and it might not work out the way you want it to. So right now I have a differential equation. I don't have an initial condition yet, and maybe your problem would have an initial condition from the beginning. But for us, let's just solve for this differential equation and find the family of curves that we're looking for. And so, separate it. So this dy over y is equal to, if there are any constants like a -1, you can just leave it on the right-hand side with the function side. This is 1 over x dx. Is that right? So let's take the derivative, or the antiderivative. So ln y equals negative ln x. Now, technically, when you take the antiderivative on the left side, you're going to get a plus c, and then you take the antiderivative on the right side, you get a plus c. But in general, since we know that there's two arbitrary constants that come out, we can put that as one arbitrary constant on one side, and that'll work just fine. So it looks like I have a family of curves now. Now, this family of curves that's given here is written as an implicit solution. Is it possible to solve for y? If it's possible to solve for y without losing any other properties or losing some negative parts to things, then maybe we can go ahead and solve for it, and then we'll have a nice equation to deal with. We'll have, I was going to say we'll have an explicit solution if we're able to solve for this. So let's take the take this as the power of e. Now let's be careful. When we deal with this, how's your algebra? By algebra, I mean intermediate algebra.
Yeah,
E to the c over x. What's e to the c? That's just another constant. So sometimes people take e to the c as another constant and just call it another constant a. Okay? So this is our family of curves. So notice it's not a plus c like we've seen before. The plus c happened up here, but then after we solved for it, it didn't become a plus c anymore. So sometimes those things can happen.
So this actually, shouldn't that be absolute value of y equals a over x?
Yeah, probably.
And effectively meaning y equals plus or minus a because
So we
the
did- we-
points below below the
So
y equals 0 are also
So we did lose some. We did lose something by going explicit. Anyways, we'll just leave it at that. I have another program here that graphs things rather quickly for me, so I'm going to use that. So the family of curves are all these curves that can be represented by different values of c. And if we take a look at our solution, kind of looks like it would fit, right? So there's a couple of important things to note here, and with respect to the existence of uniqueness theorem that we saw earlier. Notice when I move things around, we see something in the first quadrant, but we also see something popping up in the third quadrant. And if I move over here, we see something in the second and fourth. Just like the graphs that I'm seeing here, it looks like we're seeing something in the first and third, second and fourth quadrant, right? So my graphs, my family of curves, involve all four quadrants. And if I were to just copy and paste a whole bunch of these so we can see all of them at the same time, you can see the whole family. And if you draw the slope field, you can kind of see where it would fit as well. So anyways, so we have these family of curves. That's going to be the general solution. Any questions about the family of curves or general solution? That looks kind of cool. Move it around and it would be, anyways. You start seeing the fourth dimension that way. Oh. Okay. Sorry, I'm trying to work on my making this kind of neat notes. So what we have here are a family of curves. Or solution in one parameter. Right? So that's what we talked about. Now, if you have an initial condition, then you're going to restrict your curve to something. So, anybody want to pick a point? Do we want to use that same point again, 3, 2 or something? Or 2, 3, whatever it was. Let's use 2, 3. Let's go to the next page. Example continued. Boy, I'm not going to read my own writing. So now if I include this point, I have an IVP, initial value problem, with the differential equation and initial condition. And then now I could take a look at the graph again and focus or isolate myself to one piece of the graph. Now going back to that, well, let's actually solve for it. So I know that my solution is, my general solution looks like this, right? So to solve for a particular solution, let me circle this and say this is my general solution. To get my particular solution, I need to put my x value in and my y value. So if I put my y value in and my x value in there, I will have my unknown constant to solve for. And in this case, a is equal to 6. Took a while. So my particular solution, for the IVP, initial value problem that I have, which is a differential equation with initial condition, is given by y is equal to 6 over x. So that means if I focus now, if I focus my attention my solution would look like this. Now, is this correct? Is this my solution for reals? Why would I ask you that? So, is this my solution? There's something wrong here. What's wrong? What? It's not continuous. right? So the uniqueness in continuous guarantees a solution where the point exists. So although this looks like it's a graph in the first and third quadrant, I have to disregard the third quadrant solution because this cuts off over here at 0. It becomes discontinuous here. So my solution curve will only involve this positive part, 0 to infinity. I guess I should put it here. So my solution will be y equals 6 over x only from 0 to infinity, not including those negative values of x. And that absolute value that we lost earlier isn't going to matter anymore because now we're just focused on the first quadrant. Okay, the absolute value from before allowed us to go on the negative side if we needed to. Okay, if our initial condition had a negative number, then yeah, maybe we'll go over there, but it didn't, so we're just going to stick with that. Any questions? Pretty cool? Cool, huh? Until you start doing the problems, and then I said, ah, what happened? All right, I had another example, but I don't know if I want to do that one. Nah. All right, we have about 10 minutes. Let's take a peek at the next section. So the next section is trying to attack linear equations in general. So the stuff that we've been dealing with might fall under the category of linear equations, but if it's separable, then we want to separate it because that's the easiest thing to do. And if it's an autonomous differential equation, then we can also separate that. But a linear differential equation starts to get a little bit more involved, and here you have a first order, and it's linear, which means the y and the derivatives of y are not raised to any power or not taken as a function of anything other than itself. So it's just everything's linear. And then we're going to try to devise an algorithm to solve for this. So if we can somehow write our linear equation in standard forms, kind of standard form, usually standard form has 0 on the right-hand side, but if it doesn't have any of the dependent variables or derivatives, then we just move it over to the right-hand side. So this is one standard form. If we could somehow write it like this, where the coefficient of dy dx is 1, then if you focus your attention to the left-hand side and think back to the product rule. Remember the product rule? Derivative of the first times second plus the first times derivative of the second. Let's write that down. Yeah. So fg prime is equal to, let me see if I can write it like this, fg prime plus f prime g. That's the product rule, right? Did I do that right? Yeah. Okay. So if that's the product rule, and if I look at the g function in my product rule and look at my left-hand side of my standard form of my first order linear differential equation, we can pretend like the g is equal to the y function, right? So maybe we can pretend that this is y. And so now what we want to do is we just want to force the other function to kind of cooperate with us so that it makes it look like it's some sort of a g function. by that I mean we want to look at this as a function's derivative, and then looking at this as something that's the original function. So what we want to do is we want to multiply this, and they use mu. I don't know why. We want to multiply this thing by what's called an integrating factor. We want to multiply this by some function so that the coefficients of g prime and g, or the coefficients of dy, dx, and y, would fit this model where the coefficient of dy is the original function and the coefficient of y would be the derivative of that same function. So if we multiply this by mu of x, some weird function that we're going to try to find, and we haven't talked about the right-hand side, but the right-hand side is going to be the right-hand side, and we'll deal with that later. So if we can somehow turn this into f and f prime, then we can essentially make it look like a product rule. So how's that product rule going to look like? It's going to look like it's a product rule, so it must be the derivative of mu of x and y, also a function of x. Does that make sense?
How'd you end up with y of x?
Just y.
Oh, just another form.
Yeah, this is just y. Y of x. I guess we could just leave it as y.
Why not?
Because it's okay. And remember, you're solving for y, so you just integrate both sides and then solve for y, right? So now the question is, what the heck is this? Well, whatever that is, we have to, there's a relationship up here that the derivative of mu should equal to mu times p of x. Is there anything that wait, what what is this? How do we find mu here? Well, it's hard to integrate because there's a mu over there too. Why don't we
bring the, it's separable.
It's separable, right? So why don't we bring, why don't I rewrite this? Can I rewrite this? Whoa. Is that okay? What? Huh? How did that happen?
What happens when the x?
I don't know. Where's the dx? What happened? So let's divide both sides by mu. And then I have the derivative of mu over u, mu, is equal to p. Isn't that the same thing as saying the derivative of mu over mu equals p? Oh, yeah. Is that better? A little. No.
All the pieces still there, I guess that's better.
Well, anyways, I want this integrating factor, so it looks like if we just integrate both sides, we're going to get ln of mu is equal to the integral of p x dx, or mu will eventually be equal to e to the integral of p x dx. Box.
Is that going to have some values mu from that ln?
Yeah.
But you don't care about details like that.
Well, the thing about details like that is that it'll fix itself if we have an initial condition, and whether the initial condition has positive or negative values, it'll play itself out. So this is your integrating factor. You're going to take this and multiply the whole equation by this, and then finish it. So we're in the middle of an integrating factor discussion. This is your important formula that you're going to need to remember. And when we come back, we'll finish this off, do a couple of examples, and then you'll see how easy it's going to be. All right? Homeworks 1 and 1.1. Chapter 1 is due on Sunday. Okay? Sunday. 1.1. I think 1.1 and 1.2. Yeah.
Okay.
We'll give you a little bit more time for the 1.3 because it's physics.
So you're going to move 1.3 back, or leave it where it is?
Yeah, if it's there.
Everything's due to the 31st current.
Yeah,
Chapter 1.
so 1.3 is going to move.
Okay.
But 1.1 and 1.2 will be due this.
All right, those are already done, so I'm not over that.